Alright, so here we have a question about the empirical formula. Now, the empirical formula is comparable to the molecular formula. Typically, when we see chemical molecules and compounds written on paper, what we see represented is the molecular formula. Now, the molecular formula is the actual ratio of atoms that make up a molecule or a compound. The empirical formula, on the other hand, is the lowest whole number ratio of the atoms that are found inside of a compound or molecule. And the reason I say compound or molecule is compounds are made up of more than one type of atom. Molecules are made up of multiple atoms. They can be the same type of atom, but they have to have a neutral charge. But it doesn't really matter. When we're writing molecular formulas, it's the same thing. So we just count the number of atoms of each type when we have a molecular formula, and we write them on paper or wherever. So I want to start off to demonstrate this concept of the molecular formula first, and then discuss the empirical formula. So we have here a molecule of water, H2O. This is the actual molecular structure of the water molecule. And also we can see that the whole number ratios are represented. How do we know? Well, if you have one molecule of water, we write the formula as H2 because we have two hydrogen atoms and one oxygen atom. So it's H2O. So we would say that the molecular formula, will abbreviate MF, of water is H2O. So how do we derive the empirical formula? If the empirical formula is the simple or lowest whole number ratio, the simplest whole number ratio, we simply divide, okay, by the smallest subscript. So the first subscript, 2, represents the number of hydrogen atoms. The second one represents the single oxygen atom found in the water molecule. So we divide because we're looking for the ratio. Remember, when you find ratios, you're dividing. So you're trying to find the ratio. Another way to read this molecular formula is to say there are 2 hydrogen atoms per 1 oxygen atom in the water molecule. Fine. So now let's find the empirical formula of water. If we divide both by the lowest divisor, which is 1, okay, the lowest subscript or divisor, 2 divided by 1 is still 2. 1 divided by 1 is still 1. So we see that for the water molecule, the molecular formula, the actual ratio of atoms that make up the compound, and the empirical formula are identical. Okay, it's the same thing. So for water, we have a unique situation. But what about, let's take an alkane, okay? Let's take, for instance, let's say we have the following chemical formula. So we can say that here we have a molecular formula given to us as 3 carbons per 6 hydrogen atoms, or 3 carbon atoms per 6 hydrogen atoms. How do we derive the empirical formula? It's the same thing. We begin with the lowest subscript, or the lower number, okay, which would be 3, and then we divide both by this number. So C, we get 1. 3 divided by 3 is 1. And for hydrogen, 2. So now we see the empirical formula and the molecular formula for this molecule. It's different. In the actual structure for this compound, we would have 3 carbon atoms and 6 hydrogen atoms. In other words, the empirical formula gives us a ratio, okay, lowest whole number ratio of the number of atoms that are present. So we have twice as many hydrogen atoms as carbon atoms for this. Now the empirical formula, it's not as definitive. For instance, if I have twice as many hydrogen atoms as carbon atoms, I can expand this empirical formula, for instance, to say, here we multiplied by 3, but I can multiply by 5 and say, here's a 1. 5 times 1 is 5. 5 times 2 is 10. Okay, I could do the same thing with 6. 6 times 1 is 6. 6 times 2 is 12. So you see, you cannot identify a compound based on its empirical formula, but you can by the molecular formula. These are clearly different compounds, but they share, okay, the empirical formula, because the empirical formula is the lowest whole number ratio. This is useful if you're doing chemistry in the laboratory, if you're synthesizing compounds, and it's a great shorthand way to just describe a molecule by saying, hey, this molecule has twice as many hydrogen atoms as carbon atoms. But I've shown you now that for some molecules, the molecular formula is identical to the empirical formula, while for others, it's different, and the same empirical formula can actually represent multiple compounds. So now let's visit the problem that we were given. So this problem, okay, presented us with percentages. When you have percentages, it's very, very easy to find the empirical formula using the same concepts I presented. You don't need to have the actual structure or diagram. You can actually just use the numbers. So percentages, of course, we know are out of 100. 100% is equivalent to 1. So when we're given percentages, as we are here, for instance, we're told that this mystery molecule has 48.02% carbon, okay, and it has 18.74% hydrogen and 33.24% nitrogen. If we assume 100 grams, things get a little bit easier for us. So let's do that. Let's assume that we have 100 grams of our compound. If we assume that we have 100 grams, this means that we have, for carbon, 48 grams. Now notice, okay, that I am rounding my numbers to make my calculations a lot easier. Then for hydrogen, same. I would then have 19 grams of hydrogen, and rounding is fine. And for nitrogen, I would have, or I have, 33 grams of nitrogen. Now, the question, okay, the important question is, now that I have the masses of each type of element inside of my compound, how do I arrive at my empirical formula? Well, remember with the water molecule, we had H2O. Clearly, these numbers do not represent masses. They're ratios. In fact, these represent the number of moles, okay? So, or the number of atoms. And that's a very interesting concept. Here we know that we have one atom, okay, of oxygen, and we have two atoms, or two hydrogen atoms. The question is, how do we relate grams to the number of atoms? Okay. When you look at the periodic table, it tells you, for instance, that 1 mole of carbon occupies 12 grams. Okay, so what does that mean? When you, for instance, carbon, 1 mole of carbon takes up a mass of 12 grams. This mole, okay, is a quantity, as you might know, that represents the number of atoms in a substance. For all atoms, 1 mole is equivalent to Avogadro's constant, right? 6.0 times 10 to the 23rd atoms make up 1 mole. So if we want to relate atoms, okay, to grams, we use the mole conversion, because inherently we know that the mole represents, okay, Avogadro's number. Okay, so we can go from grams, okay, to atoms by using mole conversions, okay? Or we can go from grams to moles, which represents the number of atoms. We don't need to have the atoms unit because we use the mole, right? So it's the quantity that represents atoms. So now that we are equipped with this information, we can now calculate grams, which would be the mass, okay, of each element in this mystery compound. We can now calculate to find the number of moles of each. Well, you should know by heart that in 1 mole of carbon, you have 12 grams of carbon. Okay, and this is information, the molar masses that are presented on the periodic table. Likewise, in 1 mole of hydrogen, you have 1 gram. Okay, these you should commit to memory. Notice they were not provided in the question. Now the question provided the molar mass for nitrogen, but you should commit these things to memory. There's 1 for every 1 mole of nitrogen, or 6.0 times 10 to the 23rd atoms of nitrogen. There are 14 grams of nitrogen. Okay. And of course, we now do our calculations, ensuring that units cancel. So grams carbon, cancel. Grams hydrogen, cancel. Grams nitrogen will cancel as well. 48 divided by 12 is 4. We have 4 moles of carbon in this mystery compound if we have 100 grams of this mysterious compound. For hydrogen, 19. Okay, 19 times 1 is 19. 19 moles of hydrogen. And then for nitrogen, a little bit more difficult, but not that difficult, right? We have 33. You can do this quickly, divided by 14. 14 goes into 33 twice. 2 times 14 is 28. That leaves 5. 3 times 14 is 42. And we can stop here. Okay, so when you're doing empirical formulas, there's no need to go beyond, okay, 2 significant digits. That's fine, because as you'll see later, fractions have to be converted to whole numbers. So we have 2.3 moles of nitrogen. All right, so now that we have moles of nitrogen, what's next? We need to actually get the empirical formula, which is, again, the lowest whole number ratio. And as when we had, again, let's put the water molecular formula for water back up. So if this is the molecular formula of water, remember, to arrive at my empirical formula, what I did was I divided by the smallest subscript, right? I divided by 1, and I got my empirical formula, okay? Because 2 divided by 1 was 2, 1 divided by 1 is 1. I'll do the same thing here. So I know that for carbon, I have 4 moles. I know that for hydrogen, I have 19 moles. I know for nitrogen, I have 2.3 moles. The smallest of the 3 is 2.3 moles. So when I divide, okay, nitrogen, and I'm keeping my units here so that you realize that these cancel. That's why there are no units here. These are ratios. Ratios don't have units. 2.3 divided by 2.3 is 1. Okay, so in my empirical formula for this mysterious compound, I have a single mole of nitrogen so far. This might not be the end result. So if you're taking the exam, do not, or any exams, do not stop here. Because if you have any decimal, numbers with decimals, okay, you're going to have to convert these to whole numbers. So we start off with 1. We know this is the element or atom that will be represented in the lowest number of atoms, lowest ratio component. For, let's do 19. So we have 19 divided by 2.3 moles. Moles cancel. This is about 8. Okay, if you don't believe me, we can do it if you're not sure. Okay, it's about 8. We only have 6 left, so that's about 8. Okay, so I was right, okay, just in case you're wondering. And another shorthand way to do this, if you're not the best with mathematics and you can't use a calculator, you see that you have 19, okay? What's 19 divided by 2? Well, 19 divided by 2 would be 9, but you have 0.3, okay? And 0.3 means a third of 19, which is about 6. So there are ways to do it quickly. You say, well, 2 into 19 would be 9, but 0.3 is actually a big percentage, so it should be less than 9, and you could arrive at 8 that way. But it's 8. All right, so and notice that I just took 8. I didn't go any further, and that's fine because it's closer to the whole number 8. Now I arrive at 4 moles, and I divide by 2.3 moles. In this situation, okay, it's going to be very interesting. I have 4 moles divided by 2.3. Well, unlike 2.3 into 19, which is a much larger number, 4 is a lot smaller than 2.3. So I have to be really careful at this point. I should probably try to divide this as quickly as possible the correct way. Because 2.3 can only go into 4 one time. So I have to be super careful. So 1 times that, and I get 2.3. Of course, you know that you're supposed to move these things over, and I'm not doing that, but that's okay. I hope you recognize that. And you have 17 left. Okay, so you add a 0. And then I can do, of course, it looks like, remember, 6 2 is 12, 7 2 is 14. So I can do 7. Okay, 7 3 is 21. Okay, only 9 left. So my answer is 1.7. So in this situation, I actually went that far. I always recommend that if you have something that you know, a number that will be lower, a little bit larger than 1 or close to 1, then you want to. And the reason that's important is because we already have 1 down here, okay? Unless it's another whole number 1, we don't want it. But here we had such a big difference, okay? And if you have time and you're not pressed for time, you can get more significant figures if you like. So now we've arrived, of course, at these digits. And remember, the empirical formula has to be a whole number ratio. How am I going to convert these to whole numbers? Well, you need to multiply and find a way to get this to be as close to a whole number as possible. So, if we do, obviously 1 will give us identities. If we do 2 times 1.7 is 3.4. That's not the best. It's not as close. I typically say you want to get higher. Now, because this is a multiple choice question, if you went and did 2 times 1.7 and you rounded down to 3, none of the answer choices actually have that. So you'd have to go back and choose another number. So because it's a multiple choice question, you have some freedom. But 3.4 is not really a good number to round down. It's too close. It's like 1 from 3.5. Anyway, if we do times 3, we actually get 5.1. And you right away, you recognize that you round 5.1 down to 5. Now, if you had made a small little misstep along the way and you had used 1.6 here, when you multiplied 1.6 times 3, you'd have actually gotten 4.8. 4.8 rounds up to 5 readily as well, so you would have been okay. That's why I say you have some freedom with significant digits, especially because you're pressed for time. Well, we're going to go with 3. 3 looks like a great number. 3 times 8 is 24. 3 times 1 is 3. So now that we have 1, 2, 3 whole numbers, we can actually write the response to this question with confidence. So we'll say that the empirical formula for our mystery compound that started off with 48% carbon, 19% hydrogen, and 33% nitrogen will yield an empirical formula of C5H24 and N3. Okay, so this is the empirical formula for our compound.